Alright, hey guys, what's going on? So today we are talking about perturbing the Riemann and Ricci tensor within the quantum gravity playlist. And today we're going to be focusing on taking a look at what the Riemann curvature tensor looks like in terms of the perturbation of the metric. Also looking at what the Ricci tensor looks like in terms of the perturbation of the metric, and also what the Ricci scalar looks like. So without any more talking, let's get right into the content. Again, if you want to subscribe to the channel, make sure to subscribe. Also, make sure to go into my Patreon page and hit a like on this channel as well if you want to support. So let's talk now about perturbing the Riemann and Ricci tensor and the scalar as well. So if you have been sort of looking at GR, if you're interested in GR, I'm not going to go over the derivation of this in this playlist, but this is what the Riemann curvature tensor looks like. Okay, what we're going to do is we're going to ignore this part for right now. We're just, because this is somewhat of a lengthy derivation. There's a lot of indices that are going to get flipped and played around a bit, and so we're going to deal with this piece by piece. And so we're going to focus on this portion right here first, right? So this is R. We'll call this R rho. We'll call this 1 R rho sigma mu nu, and then this one over here we'll call 2 R rho sigma mu nu. So we'll deal with this guy later in the next video. For right now, let's take a look at this guy. Alright, so here's that, okay, and we're going to put a 1. We're going to put a 1 right here, okay? We'll put a 1 for all of these. And what we want to do, my apologies for the dog in the background. What we're going to do is, okay, we're literally just going to put what we found for our connection in our last video. We're literally just going to put it straight into this equation. We're going to run the numbers here. So when we multiply all this out, right, so we have, let's see here. So this d mu is going to get placed here and here and here. This d gamma is going to get placed d gamma, let's see, so these guys should be gamma, right? Or actually, no, right, so this would be a nu, right? Because we have a nu right here. So that means that's why these are all nus. Okay, nu, and nu. And we can see that these two guys are going to cancel. And right off the bat, we have an equation for our Ricci, or our Riemann curvature tensor, okay? So notice here that when we look at the Riemann curvature tensor, this is derivatives of the connection, and some things that are not derivatives of the connection. These are like squares of the connection. When we look at the perturbation here, granted, we're really only looking at the first part. Okay, this is all just double derivatives of the perturbation in the metric. Okay, and so this is what that looks like. Okay, so we got to this point pretty quick. I kind of want to get to this point pretty quick because the next thing we're going to do is use this to calculate the Ricci tensor. So the Ricci tensor is what we get when we identify rho with this index. Okay, again, the reason for that is outlined in my tensor calculus playlist and in my GR playlist. The point here, though, is that the Ricci tensor, it represents volume changes, okay, and it's a contraction of the Riemann curvature tensor. Okay, so we go everywhere, we find everywhere where there's a mu, or where there's a rho, right? So here's a rho and an alpha. Okay, so here we have an alpha. And so I've underlined these in different colors, right? So let's take a look at the blue one here. So we're not raising anything here because we don't have an alpha, okay? In the red one, right, so here we had an alpha and a nu, okay? And we also have a mu and a sigma. Okay, so what we are doing here is, so we're raising the alpha, okay? Because we're identifying rho again with mu. So we're raising the mu. When we raise the mu, we change it into an alpha. So this here is this right here. Okay? And so we can kind of see how we're doing this, right? So here we're raising a mu, okay? Because let's see here, when this gets applied, we are going to have so we're actually raising the alpha, right? We're raising the alpha, and we are going to identify that with a mu because of this right here. So we have this h here is really mu, because, and so we're going to identify that as being the trace of h, which is how this is going to be defined. So whenever we have that h mu or alpha with one on bottom, one on top, that's the trace of h, okay? And we're going to identify that with a little bit different notation, which is just this single h right here. This h right here, okay? And this h, this trace of h, is going to show up quite a bit, okay? And then we have this guy here, right? So here we are, we're raising alpha, okay? And then identifying it with a mu, okay? Identifying it with a mu. And so we get something that looks like d mu, all right? And that is the D'Alembert operator, right? So this is something you might have seen before when you take differential equations, if you understand the wave equation and the heat equation. If you don't, then I'm just going to sort of tell it to you right now, because this isn't, this is something you typically come across in like a special relativity course, okay? Or a course on waves. But the point here is that this is going to be notation for this, okay? And this, the D'Alembert, is a derivative of time derivatives and as a combination of time derivatives and spatial derivatives, okay? And that's a wave equation, right? So this is a wave equation, right? Because the D'Alembert is just this side. When we subtract this side from, or this here, to both sides, we get something that looks like this, okay? Or we can subtract this from both sides of the equation, and we get something that looks like this, okay? So this is quite interesting, right? Because what we're seeing now showing up in this Ricci tensor is something that looks like a wave equation, okay? And this is where we're going to get the idea of, since this is a wave, right? This is sort of hinting towards the idea of sort of wave mechanics in GR, okay? Then we want to start thinking about how we might be able to model perturbations in the metric as something, as like a wave of some sort, okay? Okay, so the Ricci tensor is this guy right here. Now let's take a look at the Ricci scalar. So the Ricci scalar is going to be a contraction of the Ricci tensor, okay? And so if we go ahead and do that contraction, we start off, so this is what that looks like, okay? And we're contracting, we're really just, so we're contracting this with the metric, and we're doing it with the Minkowski metric so that we can get R here. And we're going to use the Minkowski metric here because if we multiply by sigma nu minus h sigma nu, or plus, anything that, when this gets multiplied by terms in here, we're going to get higher order terms in H, and we're going to ignore those terms, okay? Because those are small. The idea here is that this H is very small, okay? So the reason, again, why we are multiplying by the Minkowski metric is because this is going to give us terms that are higher order in a really small value. And so small values multiplied by each other give us really even smaller values, so we're going to effectively ignore those. And so what we get is, okay, well, here's our Ricci tensor. And when we apply the Minkowski metric, right, we're just raising indices, okay? So we raise the nu and go to sigma, like here. Here we are raising the sigma to make a mu, or nu. And same here, raising a sigma, we can raise either of these, right? This is actually just going to give us this is just going to give us H, right? This is really just H, and this is H also, okay? These two guys are the same, so we'll add those two up. So 1/2 of this plus 1/2 of this is 1/2 of that. And then negative 1/2 of this minus 1/2 of that, well, that's just going to give us that, okay? And so I will erase some of this. We get this guy here as our Ricci scalar. All right, so we have, and we want to keep in mind also that we are doing this for just the first part of the Ricci, or the Riemann curvature tensor, okay? So we have, here's our summary, right? So we, our metric again, okay, these are just the relationship between upper and lower indices. And then we have our connection. This is our connection. We have our Riemann curvature tensor, right? That was all double derivatives of our perturbation. And then our Ricci tensor, double derivatives of the perturbation again. However, we also are now seeing wave equations show up. Okay, this is quite interesting, right? Because if you recall from our GR videos, the Ricci tensor told us something about volumes, right? So volumes, and so this is suggestive that the volumes are they evolve, or perturbation in the volume, if you will. This is the volume is evolving as a wave in some sort, because we have this wave equation taking place inside when we think of this as the metric, or when we think of things in terms of the perturbation of the metric. All right, and then the scalar as well. So this thing is areas. This talks about area deviation. And this is again something that we talked about in GR. So this is something that we talked about in GR. I've titled this playlist, as like quantum gravity for everyone. So in some sense, I'm sort of assuming that you've already taken GR, but I'll do this in sort of a way that you might be able to understand here. Volumes, you can identify a volume with two vectors, right? So you have here, I'll do it like this. Here's our manifold. Here's our manifold. And at some point, P, you have some volume element, okay? And that volume element, when we can travel in some direction, okay, and that volume element is given to us by this Riemann, or this Ricci tensor, okay? The Ricci scalar, which is this guy right here, is given to us again in GR. That we talked about this in GR, but the idea here is that our volume element tells us something about areas. Oops. And how the areas sort of deviate from flatness. So here's flatness. The area is going to be that top of the sphere in which P is at the apex of that sphere, or at some point on that sphere. Areas can be defined in terms of in that way, right, in GR. And so again, so you can sort of go to my GR playlist and sort of understand this at a deeper level if you want to. What I'm trying to do here is really just tell you that the Ricci tensor is associated with volumes, the Ricci scalar is associated with areas. And the question, and what the Ricci tensor again is, it's this object that exists everywhere in space-time. You feed it two vectors. Those two vectors tell you the direction which you're traveling, and the other vector tells you something about the radius of that sphere that's changing volume as you're traveling through that, as you're traveling through the manifold. Okay, the Ricci scalar, again, this is something that tells us something about the deviation in areas on some curved surface. Okay, and the idea here is that an area is just a number. Okay, and so if an area is just a number, then we might be, the idea here is this is a scalar field that exists everywhere. If it's just a number, it's just a scalar, then we should be able to track these areas throughout the manifold as well. Again, the details are in my tensor calculus playlist and in my GR playlist. So in some sense, I'm sort of assuming that you've sort of taken GR already, but I'm trying to do it in a way in which we're also traveling at a fast pace here, going through, not a fast pace, but a relatively fast pace, so we don't have to start from square one in this particular playlist. Okay, so that's sort of my long-winded way of saying you don't necessarily have to watch my GR playlist if you want to get through this. It might help though. Okay. With that being said though, I don't want to take up too much time here, so in the next video we're going to talk about this term right here. Right. So with that being said, make sure to hit that like and subscribe button. Make sure to hit go into my Patreon page as well if you want to support the channel and get the notes on this as well. So I'll see you guys in the next video.